In today's video, we are going to begin Unit 2, Algebra, and today we're going to talk about Topic 1 of Polynomials. Okay, so we've just finished Unit 1, and now we'll be moving on to Unit 2, Algebra, and we will finish the first section, which is Polynomials. So, some of the learning targets. At the end of the video, you will be able to define polynomials in one variable and identify valid and invalid examples. Identify terms, coefficients, degrees, and types of polynomials. Find zeros of polynomials. State and apply the remainder theorem and factor theorem. Factorize quadratic and cubic polynomials. And then verify and use standard algebraic identities up to degrees of 3. So let's begin with the definition of polynomials. So a polynomial in one variable is an algebraic expression made up of the terms involving powers of a variable, in this case x, where the powers of the variable are whole numbers, such as 0, 1, 2, 3, and so forth, and the coefficients are real numbers. So we can see in the form here that the letter n is given by a non-negative integer, so essentially only whole numbers. And recall integers themselves are positive and negative, whole numbers and 0, so we have to exclude the negative portion. And then the terms that are starting with a, such as a sub n minus 1, are what we call the coefficients, which we'll talk about later in the video, but these are any real numbers. So here are some examples and counterexamples of polynomials. Notice that in the polynomials, there are no fractions involving x, there are no square roots of x, and there are no negative powers of x. And these restrictions are very important to be able to classify polynomials correctly. So here are just some examples. Polynomials such as 5x to the power of 3 minus 2x plus 1. The value 7 is also a polynomial. Negative 4x is also a polynomial. And then some non-polynomials. So 1 over x is not a polynomial because we have x on the denominator, which is not allowed. Then square root of x, which is not a polynomial because, recall, we can write square root of x as x to the power of 1/2, and we are not allowed to have fractional powers in polynomials. Then lastly, x to the power of negative 2. Polynomials only have positive powers or 0. So the key rule here is that the exponent of the variable must always be a whole number. So let's talk about the components of the polynomial, which we call the terms and coefficients mainly. So let's take a common example, 3x to the power of 2 minus 5x plus 7. So in a polynomial such as this one, every part of the polynomial separated by a plus or minus sign is called a term. So in this case, 3x to the power of 2, negative 5x, we have to include the negative, and 7 are all terms of the polynomial. Next are the coefficients, which are essentially just the numerical parts of the terms. So we exclude the variable in the coefficients. So for example, for the first term, it has a coefficient of 3. The second term has a coefficient of negative 5. And lastly, constants are terms with no variables. So it is essentially just a number. And in this polynomial, we have one constant, which is 7. Now, understanding terms and coefficients is essential for factorization and finding zeros, which we'll discuss later in the video. Now let's look at a special case, which we call the zero polynomial. So a zero polynomial is where you have a polynomial given by p of x, in which every coefficient of the polynomial is zero, meaning that the polynomial itself is zero. So if we take our general form of polynomials from before, recall the one that had all the a's and n's in them, if we replace all coefficients with zero, we can see that p of x, or the polynomial at hand, will equal zero itself. So an important point to note here is that the degree, which we'll discuss later, the degree of a zero polynomial is never defined because there is no non-zero term to determine the degree. Now I said that, but what is a degree itself? So the degree of a polynomial is given as the highest power placed on the polynomial's variable, typically x, with a non-zero coefficient. So some examples, if we have 5x to the power of 3 plus 2x minus 1, we can see that the highest power being raised on the variable x is 3. Similarly, for 7x squared, there's only one term, but still the highest would be 2. Then next, we have negative 4x, which we can rewrite as negative 4x to the power of 1, which gives us a degree of 1. And then finally, constants, which we saw previously. A constant of the number 9, for example, basically has a degree of 0. And the reason for this is we can think of the constant 9 as the term 9x to the power of 0. Now recall from one of the earlier videos that anything raised to a 0 is equal to 1. So we just have 9 times 1, which is 9, and a degree of 0. Now degrees tell us the nature and behavior of the polynomials. So with this, we can see back at the zero polynomial that, well, here there is no really defined term. So we won't be able to determine what the degree of this zero polynomial is, because again, there is no term, there is just a value of 0. And then we give some names to different degrees of polynomials, which you'll see in a second, but here are what each of them are called. So we can classify polynomials by two different ways, by their degree or by their number of terms or term count. So by degree, if you have a polynomial of degree 0, we call it constant. If you have a degree of 1, we call it linear. If you have a degree of 2, we call it quadratic, 3 cubic, 4 quartic, 5 quintic. And there are more names such as 6, 7, 8, or 9, but they're typically not assessed and typically not asked about in math. The second way to classify polynomials is by the number of their terms. So if we have a polynomial of just one term, for example, over here, the third example, negative 4x, is just one term, we call it a monomial. The prefix mono meaning one. If we have a binomial, which is two terms, then we have trinomials, which are with three terms. So for example, we can combine both of these aspects. So let's say we have a polynomial of degree 2, and it also has three terms. Well, that would be called a quadratic for the degree, a quadratic trinomial for three terms. Similarly, we can give different names like a cubic trinomial, for example. Now let's look at what the zeros of a polynomial are, which we also call the roots in terms of quadratic polynomials. So the zeros of a polynomial given by p of x is a value of x for which p of x is equal to 0, so where the polynomial equals 0. So for example, if we have a function or a polynomial x minus 3, well, if we give x the value of 3, 3 minus 3 is 0, and we can determine that then 3 is 0 of this polynomial. Similarly, if we have 2x plus 1, well, we can simply see that plugging in negative 1/2 for x will give us 0. So the 0 of this polynomial is negative 1/2. Now, finding zeros helps us factorize polynomials and solve equations, which you'll see also later in this video. And just some more concept on zeros versus degrees. So a linear polynomial has only one zero. A quadratic polynomial could have 0, 1, or 2 zeros, and a cubic polynomial could have 0, 1, 2, or 3 zeros. So in general, the degree of a polynomial gives us the maximum number of zeros the polynomial could have. Now let's talk about the remainder theorem. So we desire to know the remainder theorem for a polynomial in order to simplify polynomial evaluation and factorization. And this provides us with a shortcut. Typically, to find the remainder of a polynomial, p of x, divided by another polynomial, x minus a, we would have to perform tedious long division. So here's an example. We define the remainder theorem as if a polynomial p of x is divided by another one, x minus a, the remainder is simply p of a. So for example, let's say we have a polynomial defined as x to the power of 3 minus 2x plus 1. We want to find the remainder when it's divided by x minus 2. Well, in this case, we see that in the form x minus a, the a value is 2. So we'll simply plug in 2 to the polynomial, and we'll get 8 minus 4, which is 4, plus 1 is 5. So the remainder of this polynomial when divided by x minus 2 is 5. So what happens if the remainder is 0? Well, if p of a is 0, we say that the remainder of p of x divided by x minus a is, of course, 0. But this means that x minus a divides the polynomial exactly. And what does this mean? Well, that leads us directly into the factor theorem. So again, if the remainder of a polynomial divided by x minus a is 0, we can say that x minus a divides p of x, or the polynomial given, exactly. So this means that x minus a is a factor of the polynomial p of x. And the reason we say this comes from integers, actually. So for example, if we have an integer of 8, one factor of this integer is 4 because it divides 8 exactly. And we share this same idea with polynomials. So here's an example of how we verify the factor theorem. Let's say we have a polynomial. In this case, it's a cubic polynomial defined as x to the power of 3 minus 3x to the power of 2 minus x plus 3. And we want to check if x minus 3 is a factor of this polynomial. Well, if x minus 3 is a factor, we know that the remainder when dividing by it should equal to 0. And then recall from the remainder theorem that if x minus 3 divides into it exactly, or if the remainder gives 0, the polynomial plugged in with 3 should give us 0. So we can test that simply by replacing all the x values with 3. So 3 to the power of 3 minus 3 times 3 to the power of 2 minus 3 plus 3 does in fact give us 0. So we can confirm that x minus 3 is a factor of this polynomial. Now let's go into the specifics of factorizing a quadratic polynomial. So let's take the example of x to the power of 2, given that it's a quadratic polynomial that has a degree of 2. x to the power of 2 minus 5x plus 6. So the first step is to find numbers whose sum equals negative 5, which is a coefficient of the x term to the power of 1. So find numbers whose sum equals negative 5 and also whose product equals 6. Now see that 6 is the constant term in this polynomial. So once we determine those two numbers, we can split the middle term, which is negative 5x, into those two numbers. So the two numbers in this case that add to negative 5 and multiply to 6 are negative 3 and negative 2. So we can split up negative 5x into negative 3x and negative 2x. And then finally, we factor out each section. So we factor x to the power of 2 minus 3x, and we factor negative 2x plus 6 to get our final answer here, indicated in green. Now let's see how we factorize a cubic polynomial. So let's say we have the following: x to the power of 3 minus 6x to the power of 2 plus 11x minus 6. So cubic polynomials are a bit more difficult because we cannot factor with the simple sum and product trick that we saw earlier. Here, the first step we can do is to try different possible zero values that are known integers, such as 1, 2, 3, -1, -2, and so forth. So we'll just try first x equals 1. So if we plug in 1 into all of the x terms, we do in fact get 0. So since plugging in 1 into the polynomial gives us 0, we can determine, recall from the theorems from before, that x minus 1 is a factor. And since it's a factor, we can factor it out of the polynomial to give us the remaining equation. And then note that the second part of this cubic polynomial that we factorized is now a quadratic, which we can factorize with this process here. The last topic is algebraic identities, and it's just recalling algebraic identities and their applications. So it's important to understand that identities are tools, not just formulas, because these algebraic identities, these common ones, help us expand expressions, factorize polynomials, and simplify calculations. So please take a minute to just pause the video and read through the following formulas or the following identities to refresh your memory on them. So this concludes today's video and topic 1 of polynomials. So today we were able to define polynomials in one variable and identify examples. We were able to identify the components of polynomials as well as the degree and types of polynomials. We were able to find the zeros of polynomials and then expand this to the remainder theorem and factor theorem. Finally, we were able to factorize the quadratic and cubic polynomials and then just refresh our memory on standard algebraic identities up to degrees of 3. So thank you for listening, and I hope that you learned something from this video.